So after all these developments took place, Niels Bohr, uh, Niels Bohr, another physicist, although it's chemistry, he's a physicist. But anyway, that's not the point. Niels Bohr, a physicist, we at that point people knew the conclusions of these various experiments, or let's say scientists knew the conclusions of these various experiments conducted, but none of them were able to devise um, a model which could accommodate all of them into it. Like we saw J.J. Thomson's model failed. And Rutherford also proposed a model which failed, but we didn't see it here. But Niels Bohr, he just proposed this planetary model, and which okay, yeah. Before this, I need to say that there was also the other experiments included James Chadwick, who tried at bombarding beryllium atoms with uh, protons, and then he obtained carbon and some stream of non-charged particles, and so that led to the discovery of neutrons. So then we got the neutrons into the picture. But and then Niels Bohr, he proposed this planetary model in which it's just like the how the planets revolve around the sun. The electrons revolve around the nucleus, which contain the positive charges, and the protons, and neutral charges, which are the neutrons. So this is the Bohr's planetary model, and well, it did it was pretty more accurate than the other models, but we still had problems with the multi-electronic system as we're seeing here. So the Bohr's model only worked for monoelectronic species like hydrogen, and then helium. Charged, doubly charged helium atom is alpha particle, but singly charged fits under the Bohr's, can be explained by the Bohr's model. And then this model could also explain Li double doubly charged lithium ion because it has only one electron. So basically, this model could only explain monoelectronic species. Then comes the model quantum mechanics model of an atom. So so yes, after during the 1930s and 40s, scientists like scientists we discovered the wave particle duality, which basically states that any particle you see around, whether you or your uh, device which you're using to see, is can be related, can be a wave also. This was given by the scientist Louis de Broglie, um, and then he state yeah he gave the idea that he found out that the every object is also a wave, and the wavelength of this objects is inversely proportional to the mass of the object, which basically means that heavy objects have a very small de Broglie wavelength, and it does not show as much as wave properties as small masses. Small masses in the sense not what we see, like you can say that relatively eraser is smaller to you, but it still doesn't have a relatively big uh, de Broglie wavelength. But when you go to this electron and protons, the atomic size, especially in electron size, this wavelength becomes so significant that they show both particle and wave nature, and this is where it gets very interesting. And there was also some other development by Heisenberg, who got this. Um, has Heisenberg proved the Heisenberg developed the Heisenberg uncertainty principle, according to which the the mass, I mean, the position and momentum of let's say, small particles such as electrons cannot be accurately determined to get, and we have to forego one of these two quantities to get an accurate value of another, which, uh, which basically means that if you want to know electrons position, you cannot know its momentum or where it will go next. And if you want to know where it will go next, you won't know its position. So due to this, the standard model which we had before, uh, we could not use it anymore. And then, so over here on the right side, we can see that the modern quantum mechanics model of atom, in which basically what this is we take a picture of the position of the electron multiple times, and we combine the picture and we get this. So this um, cloud-like picture is where you can find an electron 90% of the time, but it might even be, let's say, in the center of it, or not center, that's the nucleus, but somewhere around the atom and not in this place. So that's what that's what the modern quantum mechanics model of an atom is. This this probably requires a own video for it. This topic probably requires a entire video for itself, but then I will right now we'll have to move forward, as that lot of time has already been passed. Okay, now we'll be looking at classification of elements. So that's where we ended modern periodic table, and this is classification of elements. So elements are of uh, yeah. So we during then people found a lot of elements, but they didn't know how to classify it. So these scientists attempted at classifying it. Some Dobriner thought that uh, atoms which were three atoms. He thought in a group of three atoms, in which if the second atom is the arithmetic mean of the atomic mass of the first two atom, then it would have similar properties. Like they did have similar properties. For example, sodium, lithium, potassium, calcium, sodium, lithium, potassium, chlorine, bromine, iodine. So he thought that probably this is a general trend, but unfortunately, but for him it was not. But it was not the reality, however. But this did work for some elements, but could not explain other elements. And again, we have Newland's law of octaves, in which it's a very close theory to it's a very good, close theory to foundations of it is very close to what modern periodic table is based on, but but it did not include some of the he did not consider the possibilities of other atoms and other he only thought that each uh, valence shell can have 8 electrons basically. That's what he thought. So that's why he just classified into 8. And then yeah, it did work for some initially, but as you go beyond 20, where the electronic configuration is not as simple and the number of shells increases, this did not comply to the reality. Next, we have the more Mendeleev periodic table. So Mendeleev was came very close to building a convenient periodic table, as he um, so basically Mendeleev's periodic table is based on his property of properties such as the chemical and physical properties were functions of the atomic number, periodic functions of atomic mass. Atomic mass. Although this method was uh, it it worked really well. He even predicted that there's some elements which during his age could not be discovered using this format. So that's why we credit Mendeleev with a own element for himself called the Mendeleevium, as many other scientists who tried classifying it were not successful. And Dmitry Mendeleev has an important role in the modern in the formation of modern periodic table. Yeah, as we were talking about the modern periodic table, and this is the modern periodic table. So you can see the periodic table really well. There are a bunch of elements here, local, and this if you can recognize some of them: hydrogen, helium, lithium, helium. So The modern periodic table is after a collection of after effort of so many scientists, we were able to come up with a periodic table, but it still does not perfectly it still not does not perfectly fit all the elements in it, uh, but it does the job pretty well, like we could say. And this is the modern periodic table. So next, we'll be discussing more about it, but first I want to talk about a concept called electronic configuration. I think, yeah, electronic configuration is basically arrangement of electrons in an atom. We know the protons and neutrons are in the nucleus, in the center of the atom, as discovered by Ernest Rutherford. But the electronic configuration was a very interesting concept, as it was not based on as it was not as direct as the nucleus. Um, so first we came up with the KLM configuration. This was during the days of uh, Niels Bohr's atomic model. So we hypothesized that around the nucleus, which we see in the center of the scale element configuration, there existed energy levels in which electrons were clustered, in which electrons revolved around the nucleus, and these were circular in shape. That was an important part. So the first energy level, it had the electrons with lowest energy. As electrons gain some energy, it jumps to the next cell, and that's because it needs to go away from the positive pull of the protons. So it jumps away to the next cell, and then it reaches the valence shell and moves away from it gets freed up from the atom's control. So this is what the KLM configuration is. The first shell is K. Um, the first shell over here is K. The second shell over here is L. The third shell M, N, and then the number of electrons in each of these shells is determined by 2n square. So the K shell had 2 into 1 square, which is equal to 2. Then L shell had 2 into 2 square, which is equal to 8. M had 3 into 2 square, which is equal to 9. And N had 4 into, sorry, 18. I'm very sorry. 18. And then 4 into 2 square, which is equal to 4 into, sorry, this is a mistake from my side. I apologize for it. So the as I told in the disclaimer, if you that I might make mistakes, and I made one here. Yeah, so m square has 2 into 3 square, which is equal to 2 into 9, which is 18, and n had 2 into 4 square, which is equal to 2 into 16, which is 32. So that is how we had an electronic configuration. And this was the this was the for standard model, but as we moved on, as time passed by and we got the modern quantum mechanics model, we discovered that there was more to this electronic configuration than just SPDF. Than just KLM. So we got this SPDF configuration. So SPDF is not exactly saying where the position of atom is, but electron is, but just says where the more than 90% of the probable uh, times it could be. So the S shell looks like a circle. The P shell just looks like two loops. If you're drawing it, it'll be something like The P shell just looks like two sacks. I mean, there's actually three of this. And then the D shell contains four sacks and F shell contains eight sacks. Yeah, that is SPDF. And then this is how it will look in an atom. So these clouds are called probability clouds. You can see clouds, or we call them probability clouds, or these balloon sort of figures. So these are where the electrons could be, like, in most possible times, but it could just be somewhere else also. That is the I would say wickedness of quantum mechanics. You can't really determine where it can be at a given point in time. So these are the most probable times, more than 90% probability. 90% of the time, the electron we're looking for will be somewhere over here. That's what this model says. So yeah, as I told, we'll again be talking about the periodic table. So first, first I'll just tell something more about this SPDF configuration. So when we look at the periodic table, yes, we got it. When you look at the periodic table, you can see that it looks like some Australia-shaped figure, but and it might be difficult for some people to remember it. But this is how this periodic table. It's easy to remember if you know the SPDF configuration. So first, for yeah, so in SPDF configuration, the S shell can hold two electrons. The S shell can hold two electrons. The P shell can hold six electrons at max, and the P shell can hold 10 electrons. F shell can hold 14 electrons. This is the basics of SPDF configuration. And how we'll fill the shell, there's a method for it. And I'll just tell it for simply, I'll just tell it for fun. But you don't need to know it right now. First is, yeah, so like we talked, the SPDF is just a subshell. They're not exactly like KLMN. They're just subshell configuration. The one we denote here can be taught like K, but in that K we have, yeah, one is two, then which basically denotes that hydrogen and helium, because the first energy level the one denotes energy level. So second is 2s2, which denotes lithium beryllium. So second energy level you can hold two electrons, and 2p6. So in the second energy level you can also hold 6p electrons. That's why as I think, yeah, I forgot to mention this, but the periodic table, some characteristics of the periodic table is that the groups, it has 18 groups, 7 periods. So each of these groups can denote the number of valence and electrons it has. The number of periods could denote the energy level of each electron, energy level in which the each valential electrons are. So valence and electron, the group could denote the valential number of valential electrons, and then the period could denote the energy level in which they are at. Yeah, that's what I meant. So that is one good characteristic of this modern periodic table. So yes, we'll continue with that SPDF. So next we'll have a 3s2, 3s2, 3p6, and 3d10. Then we'll have 4s2, 4p6, Yes, so got disconnected. So then we have a 4D10 and 4F14, 5S2, 5P6, 5D10, 5F14, 6S2, 5D, 6S2, 6P6, 6D10, 6F14, 7S2, 7P6, 7D10, 7F14. So yes, so then how the electrons get filled is uh, we can we can just easily draw diagonals like this to just figure out how electrons in these orbitals get filled. So first will get filled in 1s or 1s orbital, then second will get in 2s orbital, then it'll get filled in 2p orbital, then it'll get filled in 3s orbital. So it's like that. It goes on like that. This is how the electrons are filled. So yes. So moving forward, now I think we can discuss the periodic table and some properties of it. So in this periodic table, you notice that the first there are two elements. You can think of it like these are the S shell. These are elements which has their valence electrons in S shell, and this we can see there are a bunch of six. This There are 7 periods with 6 electrons in each of them. Yes, and you can see there's another division of this. There, we learned it as transition element, and then some protruding part which cannot be fit into this Australia map. New Zealand, although New Zealand is towards the right side of it, you can think of it something like that. Yeah. So this is how the periodic table is, and the recall that we discussed, the S shell can have two electrons, so two valence electrons. So these elements are filled with those two valence electrons, and yeah, we can, and this comes in the left side, and then the recall the P shell has a six can accommodate six electrons, so there are six elements always in this side where we have most of the non-metals, and towards the left we have the basic metals. Towards the right side we have the non-metals, and in the center we have transition elements. Transition elements is because you can see there are 10 elements over here, so the 10 d orbital, I mean the d orbital can hold 10 electrons, so that's why we have 10 over here, 10 elements over here. And then below the F, these are the elements which have valence electrons in F shell, and there are 14 in each row, as you can see. And then, so that's why these are F block elements, basically. This is the S block elements. P block, D block elements and F block elements. Okay, so here's something I want to discuss with you. You would have heard people calling this the transition elements. Why is that so? That's because that in these metals, as you can see, in the first 20 elements, the first energy level, an orbital from the first energy level, 1s2 2. So let's just do the calculation here quickly. So 2 electrons, and then second is 2s2 plus 2, and then third is 2p6 plus 6. So fourth is 3s2. So remember, the top number denotes number of electrons in each of these orbitals. Yes, in the bottom number, these are just the bigger numbers which I wrote is just the energy shell. I mean the energy levels. So next one is 3s2, which is 2. 1s2, 2s2, 2p6, 3s2, 3p6. This is 6 electrons, and 3s2, which is 2 electrons. So 2 plus 2 plus 6, 10 plus 2 plus 2 plus 6, which is equal to 20 electrons. 20 electrons. So first 20 elements, they have the valence shell goes in an increasing order of energy levels. So hydrogen, helium have first, then first energy level, then lithium, beryllium, boron, carbon, all of them have, until neon have second energy level, like KLM. I could, like what we learned in KLM basically. But as we go from the 28th element, uh, we see that the we see that 3D shell, I mean the 5s shell gets filled before 3D shell, or 4s shell gets filled before so 5s shell gets filled before the 4D shell, and 4s shell gets uh, filled before the 3D shell. So that basically means that in the it's we can explain it like the penultimate shell has some electrons left, but the final shell has electrons. So it's like the second last shell of this inner transition of this transition elements have their second last shell not completely filled, but they still have electrons in the last shell. What I mean is, imagine if there's an element in our KLMN only, which has an electronic configuration 262. You could say that you would have an doubt. It will be like, how can they have two electrons in the valence shell before that gets filled in the penultimate shell? So that is the reason. But in these electrons, I mean in these atoms, that's how it works. So that's why they are called transition elements. And in the second last, I mean, you can see this protruding F block elements. They are called F block elements because two shells before them don't have completely filled subshells, but they still have electrons in the second last shell and last shell. So that's why they're called inner transition elements. And these elements, you can say, why can't we just accommodate? Because they all, because of the property I spoke to you about, that the inner shell does not get filled, but the outer shell gets filled. All of these elements have 3D. I mean, the 3D, all of them have their valence electrons as 3D. So how can we fit all of them into the periodic table? It will disorient it. So that's the reason we just put them below. So all of them have a, you can say, a valence. Yeah, they all of them have 3D electrons, but we cannot fit them over here because it will just disorient the periodic table. So in the first few elements, it's very straightforward, as we could see, but as we go into higher atomic numbers, just like radioactivity, the stability, I mean, I wouldn't say they're not stable, but many of these atoms are not stable, and um, it's not very straightforward like what we learn. So yes, I hope you understood, all of you understood. Um, so, um, so let's. I'll just do one more quick topic, although running out of time, which was assigned. But anyway, this is just about how we can denote element in the SPDF configuration. So let's take oxygen. In KLMN, we denote it as 2, 6 because it has an atomic number of 8. In SPDF, what we do is we write it in this order. So first is 1s2. So notice, wait, 1s2, 1s2. So oxygen, 1s2. Then we have 2s2, and then so notice only the top number denotes number of electrons. Okay, this is just the energy level. One is first energy level, two is second energy level. That's like the shells we can talk. Energy levels are like the shells. This is the first energy level, second energy level, then third energy level, etc. So 2s2. So 4 electrons are already filled, but we need 8 electrons totally. 2 plus 6 is 8. So we go to the third one, 2p. In 2p, in 2p, we only need to fill 4 electrons to obtain oxygen electronic configuration. So this is the electronic configuration for oxygen. So that's how we can determine it. We just go by this order and look at the number of valent electrons. So yes, that's how the electronic SPDF configuration works. And remember, these are just probabilities. They're just where you could find it. You don't have to find it in one S shell. You can find it somewhere, even out over here. I would say it's not. If it's not here, you could just find it here also. But mostly you'll find it here, like 90%. And yeah, I think yeah, that's it for today's class. No, remember that I know I've not been very clear, but as as we go forward, as we do more classes, um, I'll be more experienced. Teaching is not very, I mean, not explaining is not very easy, I would say. And yeah, if you, yeah, I might have made a mistakes here and there. Uh, because yeah, I was nervous a little bit, and there was a little bit of problems, technical problems here also. But I might have made some mistakes, and I don't want to like I don't want to give wrong information to people. So if you notice them, just tell me, and I'll try to convey to all my viewers somehow. And that will be the end of the first class. So next class we'll be looking at the syllabus. I'll be just trying to explain whatever's there in the syllabus and see if I could do it. And that's the end of today's class. Thank you, everybody. Have a good day.